In this video, we'll cover the basics of series termination following on from the previous video on parallel termination basics. The 4 boards you're seeing here, which are predominantly fairly high-speed digital boards, make use of series termination in many different aspects. Be that, for example, the top right board, which has an Ethernet physical layer IC. A lot of these resistors you see around it, as we'll see later as well, are actually series termination resistors. Or, for example, this Spartan 7 FPGA on the top left, which interfaces via I2S with this codec. Some of these resistors are also series termination resistors. The question is, why do we need them, when do we need them, and how do we size them? All of this, along with simulations and practical examples, I'd like to cover in this video, and also explore some further resources to dive a bit deeper. A huge thank you to Altium for sponsoring this video. Make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium Designer free trial, as well as 25% off your first license purchase, and you can check out all the cool features, including Altium 365. Please visit the link in the description below to learn more about Altium 365 and many of the core features, such as ECAD, MCAD integration, library management, design reviews and markups, and much, much more. Octopart is also a part of the Altium ecosystem, so make sure to go to octopart.com, which allows you to search for millions of components across hundreds of component distributors very easily. A huge thank you to PCBWay for sponsoring this video. The boards you just saw at the start of this video were manufactured and assembled by PCBWay in China. These are fairly complicated boards with very narrow features, such as 100 micrometers, high layer count boards with controlled impedance, and they did an absolutely fantastic job, and I'd highly recommend you try out their services. For those particular boards, I went with their advanced PCB service. At the time of making this video, the PCBWay project design contest is also live up to January 2024, and I'd strongly suggest participating with your own designs. There are various prizes available, and further details can be found in the link in the description below. If you haven't already, make sure to check out video number 119 on my channel, titled Parallel Termination Basics, as some of the topics have already been covered there, for example, why we need termination, when we need this, as well as looking at the basics of reflections. A lot of this I won't repeat in this video and skim over some details, so make sure to check this video number 119 out first. It will skim over some of the basics again here. When we're talking about termination, in this case, I will refer to termination with respect, for example, high-speed digital logic. There's, of course, termination also with RF designs and other designs, but effectively, the boards we'll be looking at and simulations will be concerning high-speed digital logic. High speed, very hand-wavily speaking, means we are assuming short rise and fall times, so fast edges, and comparatively long transmission lines. We'll look at a basic structure at the top right side where we have a driver which has a certain output impedance ZS that emits a signal along a long transmission line which has its own characteristic impedance ZTL or Z0, and then is picked up by a receiver or load which has its own impedance ZL. As we saw previously, mismatches between the driver and transmission line, between the transmission line and load, mismatches within those impedances will result in reflections. This in turn will give us overshoot, undershoot, ringing, and so on. This will give us signal integrity problems. For example, we might exceed maximum ratings, we might drop below certain logic noise levels or margins, we'll get EMI problems, for example, ringing, increased frequency content, and more. The reason we then use termination is to effectively match impedances, and therefore reduce the magnitudes of these reflections. That in turn hopefully mitigates some of these problems, for example SI problems, EMI problems, and in turn allows us to run our systems, for example at higher data rates, allows longer line runs and more. There are many types of termination possible. We've already covered parallel in the previous video, and in this video we will be looking at series termination basics. In the previous video, again, we looked in reflections in quite some detail. What was important is that we remember, at least in part, this reflection equation. This reflection equation effectively looks at a boundary, for example, the boundary between load and transmission line, that impedance boundary, and says, depending on the mismatch, what percentage reflections do we get, and are they positive going reflections or negative going reflections? What will be important in this video is first of all the matched case, so when the impedances are matched, we get no reflections, and we will also need to remember positive going reflections. For example, if the load impedance is higher than the transmission line impedance, at that boundary, we will get positive going reflections. So the reflection adds to an incident wave. Again, I'm rushing through this, please check out video 119 for more detail. Our typical digital setup, as we've seen before, might be a driver. This could be an output from, for example, an FPGA with fast ed rates. we send a signal down a transmission line, and that might be picked up by some sort of receiver, a load. Typically, a driver will have its own impedance, the transmission line will have a characteristic impedance, and the load will have an impedance. Typically, the driver and the line impedance is much smaller than the load or the receiver impedance. So typically, the driver or the output impedance of the driver might be a couple of ohms, a couple tens of ohms. The transmission line, typically around 50 ohms. Of course, there are variations. And the load might be in the kilo ohms or even mega ohms. Then, for example, the boundary between transmission line and load, where we have this large change from 50 ohm impedance to kilo ohms or mega ohms impedance, remembering back to our reflection equation, this one here, we can see that we will get large, pretty much 100% positive reflections at this load transmission line boundary. The question is, how do we mitigate that? Previously, we saw an option might be parallel termination resistors, but there were quite some downsides to using that, and oftentimes not possible. The reasons being, for example, needing strong drivers, increased power consumption, needing extra reference voltages, and so on. Therefore, in comes series termination, and this is an incredibly common termination technique. Again, the solution is one of many. What we do, very simply speaking, to start off with, is adding a small series resistor after the driver output and before effectively we go into our transmission line. So a simplified diagram might be like so. We have the driver generating a signal through its output impedance. Straight away we place a small series resistor that then feeds the transmission line. We then hit the load, our receiver at the end. Let's go through what happens in this scenario. Assuming we choose our termination resistor RT approximately equal to the characteristic impedance of the transmission line minus the source or the driver output impedance. Keep in mind, if we choose RT to be Z0 minus ZS, then adding RT and ZS together means we get the characteristic impedance of the transmission line. So ZS plus RT equals Z0. So once we launch our incident wave from the driver, we send a signal, which we want to send towards the load. ZS plus RT, the output impedance of the driver, and the termination resistor, together with the transmission line, form an equal valued potential divider. So for example, if our incident wave has a 1 volt low to high transition, at the transmission line boundary, effectively see, because of this potential divider, 0.5 volts, so half that. Then this wave travels down the transmission line and hits the load. This is step 2. Once the incident wave hits the load, remember that the load impedance is far greater typically than the transmission line impedance. We get a reflection, and pretty much 100% positive reflection, which is sent back down the line towards the driver. This reflected wave adds to the incident wave to give the full amplitude. The nice thing is also, because this reflected wave on its way back sees ZS plus RT, which is equal to the characteristic impedance, we actually don't get any further reflections after this round trip. You can see this in the top right side in the image. The blue curve is the output of the driver, the red curve is the input at the load. Remember, we have a 0 to 1 volt transition at the driver output, but due to the potential divider, we actually get half that voltage until we hit the load. The 100% reflection goes back and adds to the incident wave, where the reflected wave adds to the incident wave, and we actually double the voltage again back to 1.0 volts. This is what's seen at the driver end, but the load end actually sees the red curve, so just a fairly clean 0 to 1 volt transition. This we should keep in mind, that the waveform is only fairly clean at the input at the last load, and anywhere between that, we're going to get, let's hand-wavily call it, a somewhat messier curve, so similar to this blue curve, where we have delays before we get to our maximum amplitude. The way series termination works is known as reflection mode switching, and quite a clever technique. All in all, what we have to remember is that we want to match the driver plus the termination resistor impedance to the transmission line impedance, and effectively, very simply speaking, let the reflections take care of the rest. As with parallel termination, the question is, when do we need this? I'll give you some practical examples and we'll look at some simulations later on, but very simply speaking, this depends on rise and fall times, transmission line lengths, and so on. I'll leave a link to this in the description below, but I'd strongly suggest checking out application note AN903 by Texas Instruments, which goes through some termination techniques in a bit more detail. I'll also leave a link to Dr. Howard Johnson's site on series termination resistors, as well as a link to practicalee.com if you'd like a bit more information and a bit more thorough explanation on series termination. Thinking back also to parallel termination, where we needed pretty strong drivers, we had a higher current consumption, series termination is great in that sense because we don't really need strong drivers. We've just added a small impedance to the output of our driver, We're not pulling a small termination resistor to ground or some other voltage, which means we have fairly low power and not really an increase in DC current. So we can use pretty weak drivers with series termination. The magnitude of RT, so our termination resistor, can be sometimes a bit hand-wavy and difficult to find out, predominantly because we're often not really sure what the driver output impedance is. The transmission line impedance is fairly well controlled. Usually we'll get a 10% tolerance from our manufacturer, and the load impedance, as long as it's significantly larger than the transmission line impedance and the driver impedance, we're safe in any case. The tolerance of the termination resistor, of course, also plays a part, but again, the most difficult aspect of this is finding the driver impedance. Once we have the driver impedance and the transmission line impedance, we simply have to use this RT equals Z0 minus ZS equation. Keep in mind that the driver output impedance will probably depend on the loading, it'll depend on the driver type, depends if it's on a high to low transition or low to high transition, and so on. Again, make sure to check out this article by Dr. Howard Johnson, and he'll go into more detail on sizing this series termination resistor. Additionally, you can find driver output impedances from IBIS models, or at least ballpark values, and I'll leave a link to this in the description below. This is a nice blog post by Bert Simonovich, who goes into quite some detail explaining how you might extract output impedances from drivers using IBIS files, which are typically available for free and openly from manufacturers. In any case, as we'll see, I'll show you some guidelines when we go through some practical examples as well of how I might go about choosing the termination resistor value. In any case, it's typically good to put in a placeholder low value, as we'll see. Some other issues that arise with series termination might be that it's pretty much point-to-point only. As we saw, because of this reflection mode switching along the line, we're not going to get these clean voltage levels or these clean transitions that we might see at the load with this type of series termination. Additionally, we have somewhat of an RC low-pass filter effect. We have these series resistors plus the line and load capacitances, which will reduce the edge rates, reduce the slew rates. Also, there might be some increased settling time. Remember the round trip delays, there are reflections involved and so on. And these are things we need to take care of as well. Placement I'll show you in practice as well, but very simply speaking, the placement of the series output termination resistor should be as close as possible to the driver output. If not possible, it should be within a lumped distance of the driver output, again to do with critical length, which we mentioned before. As examples, and again I'll show you more of this in Altium Designer, here's an Ethernet physical layer on the left-hand side, which has several transmitting lines, so drivers, in this case these green colored traces and components. We're going out from the physical layer, and as quickly as I can, fanning out, of course I need some space to fan out, I place my series termination resistors very, very close to the driver outputs. On the right-hand side, this 4-pin package is actually a crystal oscillator, and pin 3 of this package is the CMOS oscillator output, which feeds very quickly into a series termination resistor. You can see pin 3 of the CMOS oscillator to pin 1 of the resistor. That trace is very, very short indeed. You can, of course, also use series termination resistors on bidirectional lines. Then we will need a termination resistor at each transceiver end. Now let's go over to Altium Designer to look at some simulations and some practical examples of how I might size and place these resistors. Here we are in Altium Designer. Now I've just generated a very, very simple schematic and PCB to demonstrate some of the signal integrity tools and how we can use series termination to our advantage. In effect, I just have a CMOS oscillator driving some very simple buffers, some very simple drivers. We have these transmission lines, and then they reach at a fairly high impedance load. The actual part numbers are relevant. We can play around with different logic families. What's important, or the very simple structure, is that we have a driver, transmission line, and load. On the PCB, this is fairly exaggerated. We have our driver here, various transmission lines where we can vary the lengths and characteristic impedances, and then we have a load at the other end. To check out, for example, the reflection waveforms and how adding series termination resistors might help, we can go to Tools, Signal Integrity, and we can assign various models, so logic family groups, to the drivers and the receivers. So we can select different, for example, logic levels, different rise and fall times, and so on. I've just assigned the LVC type logic family to the driver, as this has fairly fast rise and fall times. Then looking at, for example, this first trace, so coming out of the driver, going along a pretty long transmission line, this impedance is about 50 ohms of the transmission line, and into the receiving end. I've used the Altium Designer stack-up tool to calculate a trace width of about 0.3 millimeters for this particular stack-up to give me an impedance of pretty much 50 ohms. Now we can examine what the waveforms look like, for example, this top transmission line. and this was buff out 1. If I double click on this, it gets added to the netlist on the right hand side, and for now I would just like to plot the reflection waveforms without any termination. Then I can click on reflection waveform, and this is what we see. And this is a classically unterminated line. The bottom blue trace is the driver output, the top red trace is the receiver input. At the receiver input, we can see we have quite a bit of overshoot, so this should be nominally 3.3 volts for logic high, so we're overshooting to about 3.6-ish volts. We have ringing as well, which is effectively an EMI problem because we get increased frequency content, and we get this both on the rising edge as well as on the falling edge, so that isn't great. The nice thing is about the signal integrity tool is that I don't have to add in a series resistor here and play around with different values. What we can do in the signal integrity tool is on the bottom right hand side under termination, we can select different termination techniques, and I'll select series resistor, and we can do a sweep of series resistors placed into the PCB without actually making any changes ourselves. This is very nice, and we can see the diagram already indicated on the bottom here. We can sweep through different values, so we could start from very low series impedances to even higher than, for example, the characteristic impedance of the transmission line. So let's just go with this and click on reflection waveforms. And this is what we get. Remember, no termination, we got these waveforms at the top. We're interested at the load side. So at U2, which are these sets of these third graphs. So a 10 ohm termination already looks fairly decent. We have some delay before we reach the 3.3 volt level. And as we increase the series termination values, so to 22.5 ohms, to 35 ohms, to 47.5 ohms, to 60 ohms, and so on, what we can see is that the edge rates are reduced significantly or rounded off significantly. However, even with these low resistance values, so for example 10 ohms of the output impedance in this case, if we compare that to the node termination case, we've already gotten rid of the ringing, and we pretty much have a critically damped system even with fairly low resistor values as our series termination. So a pretty effective method using very small series termination resistor values. Again, this is a pretty hand-wavy demonstration. We don't really know what the output impedance is. We're choosing logic families fairly randomly, but I hope this illustrates how quickly, and even with small resistor values, you can make quite significant changes on, for example, the reflection waveforms. And as we increase the resistor values even higher than the characteristic impedance, we get quite drastic reduction in edge rates, and it takes far longer to settle for this waveform. Now let's look at some practical examples with regards to sizing and how you might go about this, especially if the driver output impedances are unknown, as well as placement of these series termination resistors. This is the Z breadboard, which is part of one of my advanced digital hardware design courses via Fedivel. Links for that are also in the description below. But this board, for example, which we also saw at the beginning of this video, uses quite a few series termination resistors. For example, between the zinc system on chip and the gigabit Ethernet physical layer, or between the zinc and the USB high speed, or even, for example, between the zinc and the QSPI flash memory, which might be considered at lower speed, very simply speaking, than, for example, the gigabit Ethernet. What you'll see with series termination is, unless you look at IBIS files or models and simulations, that it can be rather difficult to pick precise values for series termination resistors. To show you that, I've just picked out some random, for example, gigabit Ethernet capable physical layers, gone to one of the data sheets, and we can see, for example, for certain pins, they've included actually series termination resistors on certain gigabit Ethernet GMII lines, but the output impedance varies quite considerably. It can be 35 ohms, it could be nicely 50 ohms, which might be our typical transmission line impedance, could also go up to 65 ohms. Another example is a different gigabit Ethernet physical layer. So we have a DC output impedance for single-ended mode might be between 40 and 140 ohms. Then looking at, for example, the AMD Xilinx Zinc system on chip, looking at their PCB design guides and application notes, sometimes you can find different impedances depending on the drive strength settings you set within your system on chip or FPGA. So here there might be an output impedance of 25 ohms. A different one might be dependent on some sort of calibration resistor, might be dependent on the slew rate setting, and so on. So unfortunately, it isn't particularly straightforward to choose series termination resistors. Therefore, a simple guide, I would say, is if you're aware that you potentially might need series termination resistors, for example on high-speed digital lines where you're expecting long trace lengths, I would put placeholder series resistors in any case, and these could be either 0 ohm resistors, these could be 10 ohm or 22 ohm resistors, a fairly low value that at least you have the footprint in there, at least you have the component in there. If you do run into problems, you can change out the value and measure on an oscilloscope what your waveforms look like, but it doesn't mean respinning your PCB design. That's why I put on high-speed digital line, for example, this gigabit Ethernet physical layer, pins 22 to 27 are outputs, and on the schematic, also indicating very close to the outputs of these drivers, I put these template, let's call them 22 ohm resistors. For many designs, I've found this kind of order of magnitude series termination resistor to work very well. So again, it's a template value. Unless you've gone through the modeling process of IBIS files, simulation, and so on, I would put them in any case, if it's on clock lines, high-speed digital lines, and so on, already indicating in the schematic that these are close to the outputs. Similarly, also for example, CMOS oscillators. This is a 33.33 MHz CMOS oscillator. Now the frequency isn't important as such, but the rise and fall times are important. You can estimate the rise and fall times to be about 10% of the period of the clock, very roughly speaking. So the faster the clock, typically you will need faster rise and fall times. Therefore, also at CMOS oscillators, I'll place a template, let's call it a placeholder series termination resistor, again close to the output, placeholder value, and then measure on the physical PCB if I do need to change the value, or if I can get away with, for example, a 0 ohm resistor. Again, the precise method is doing simulation using IBIS files or other models you have available. Then when it comes to placement, as we saw previously and very briefly, for example, for this gigabit Ethernet physical layer, these green traces are outputs, the driver outputs, very high-speed digital lines, so we have controlled impedance traces, and as quickly as we can, or as soon as we can, I place these series termination resistors very, very close to the package, very, very close to the output. Of course, I can't place these arbitrarily close, so the ideal situation might be something like this, but then again, I need space to fan out, and that's why I have to place these series termination resistors further away. But remember, these connections should be as close as possible or within a lumped distance from your output to your series termination resistor, and then you can have a fairly long transmission line which goes over to your receiving end. In this case, it's the AMD Xilinx Zinc system on chip. So fairly straightforward to deal with these series termination resistors when it comes to placement. Thank you very much for watching this video. I hope it was interesting and gave you a basic overview of series termination, how to approximately size your termination resistors, what to pay attention to, and when series termination might be useful. If you liked the video, please do leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest videos on hardware design and embedded systems. Thank you very much for watching, and I hope to see you in the next video. Bye bye.